Leibniz, Hanover. Mr. Hanover, please, Wolfram.
Yeah, so thank you very much for the invitation. It's very nice to give a talk here. So I think I started joint work with Nikolai around 9 years ago, and by now we have 10 papers, so almost one paper a year in average, but lately it's more difficult to do joint research. And I have to say, has been always a great pleasure and a big value for me to hear Nikolai's idea, and also what I want to explain today. There are many of Nikolai's ideas inside, and I think it's somehow connects some topics of what we heard already during the conference. So it was very nice also to see this very general framework of Toeplitz operators. Here I will do more or less the opposite and look at Toeplitz operators in a very classical setting, mostly in this case of the Fogg-Barkman space. So the domain is the Cn or maybe the ball. But most of these, or a big portion of these results, also generalize to bounded symmetric domains, and the ideas are rather similar, but the proofs become a lot more technical. So what I want to do is to first start with some kind of simple approximation problem, and then give you a few applications of this. So this is a topic just on functions, and I want to apply this to Toeplitz operators. First, the problem of boundedness, some simple result I want to show here. Then I want to talk about the deformation estimates for Toeplitz operators, and finally, I want to apply all of these things to a certain type of Toeplitz algebras over the two-dimensional ball. And also these things will generalize to higher dimensions. So that's my plan today. I hope I can get through everything. So let me start with a very simple question, which probably most of you can easily answer. And here I want to consider the space Cn, and I want to consider uniformly continuous complex valued function on Cn and Lipschitz continuous functions on Cn. So the first space, Lip, is the space of Lipschitz continuous function, and UC means uniformly continuous functions. And certainly one is bigger than the other, so the Lipschitz continuous functions are contained in the uniformly continuous functions. And another observation is that, of course, both spaces contain unbounded functions. For example, just linear functions are contained in both of them. And then we can also look at the bounded uniformly continuous functions. This will be the space BUC. So this is certainly a subspace of all uniformly continuous functions. And if you look at this inclusion star here, you may ask whether this inclusion actually is uniformly dense. Or in other words, if you can uniformly approximate uniformly continuous functions always by Lipschitz functions. And if this is the case, how can you do this in a reasonable way? And that question has a very general answer. Here we're working on Cn, but you can ask this question, of course, in a very more abstract setting. So think about a metric space, X with a metric D, and then we call this metrically convex if the following condition is true. So if you take two balls, B of XS, X is the center of the ball, S means the radius with respect to the metric, of course, around X and Y. These are 2 points in X. And then the condition is that they intersect if and only if the distance between the centers of these balls is smaller or equal S plus T, the sum of the radii. And if you think about this condition, then probably every reasonable configuration would be of that type. And in fact, for example, complete Riemannian manifolds are metrically convex, so that looks like a very natural condition. There are metric spaces which are not metrically convex. For example, you can get or you can define certain unit spheres in certain Banach spaces which do not have this property. However, if you have a metrically convex space, then it is well known that Lipschitz continuous functions are uniformly dense in uniformly continuous functions. And if you want to see a proof, you may look at this book here by Beniamini and Lindenstrauss from 2000. And there's very recently very nice and short paper by Lou Coburn where he discusses approximation by Lipschitz functions from this year. You'll find it on arXiv. Typically, approximation of uniformly continuous function, as you may imagine, by Lipschitz function is done by somehow piecewise linear functions. So they are continuous, but maybe not very smooth. They may have some points where you can not differentiate. So you may ask, in this very simple setting of where the metric space is just Cn, can you do a bit better? So can you approximate maybe even by real analytic Lipschitz functions? And how can you control the remainder? And if you think about this problem on Cn, if you want to approximate something by functions which are very nice, then probably you will immediately think about a convolution by some good kernel, and that works well. And you can look at the heat transform. So you take a function and you take a convolution of that function with the heat kernel, which is this exponential here. You can do this for some parameter t. T you may think as a time parameter, t is positive, and then you get what I denote by f twiddle of t. This is the heat transform of f at time t. And this comes from the heat equation. It's well known that that transform has the semigroup property, which is the condition written here. So here, I do not assume that this function is bounded. It might be unbounded. So this integral may not exist for all times t, but the semigroup property is true whenever it's well defined. So we can use this to define certain function spaces. The first object I want to introduce is the mean oscillation. So if I take a function f and t bigger than 0, w in Cn, and then I form a new function MOTFW, which is formed by this difference here of heat transforms and absolute value square of heat transforms. And even so, there's a minus in between. You easily check that coincides with what's written in the last line, and that's certainly not non-negative, because the heat transform is a transform with a non-negative kernel, and it maps non-negative functions to non-negative functions, and what's written here is a square of something. So that gives a function. And with this function, we can define the space of functions having bounded mean oscillation. So this is the space BMO index T2. So these are all functions with the property that function MOT, the mean oscillation, we take a square root of this, so it's a real valued, positive valued or non-negative valued function, and you take the supremum of this, that this is bounded. And here a few remarks. First of all, this index T here is not necessary, because this condition here is independent of T. T was this time parameter in the heat transform. And these are actually also vector spaces, so these are linear spaces. They are independent of T, so we omit the T here in the index and just call them BMO2. However, of course, this object here, which is a semi-norm, it's not a norm, it's a semi-norm, this depends on T, and we will use this quantity, and we will use this dependence on T later on. And now we have a certain inclusion of spaces. So we had the uniformly continuous functions. They, of course, contain the bounded uniformly continuous functions. And then we can also look at the L2 space of Cn with respect to this family of Gaussian measures. T is anything bigger than 0. And then in between UC and L2, we find this space BMO2. It's squeezed in between. In particular, since uniformly continuous functions contain unbounded functions, the same is true for BMO2. So this also contains unbounded functions, but they do not grow too much at infinity. There's another space which plays a role, and these are the functions of bounded oscillation. So this definition here is maybe not the definition you find at the first place, but there's an equivalent formulation. So if you look at continuous complex valued functions on C, then they are of bounded oscillations if they fulfill this kind of inequality here. It's not a Lipschitz estimate, you have a constant C here. So if such a C exists, then these functions are of bounded oscillation, and this space is denoted by BOCN. And again, we have an inclusion. So functions which fulfill this inequality on the third line, they're all in BMO2. And actually, you can decompose the space of functions having bounded mean oscillation into the space BO and some space which is denoted by BA, meaning a bounded average. And you can do this with the help of the heat transform. So this is the decomposition, what you see in red here. Of course, that's not unique. You can do this for any T. For any T, this gives you a decomposition. And what is BA? BA means a bounded average, as I said, and that means that the heat transform of absolute value of f squared is a bounded function. So that's a rather strong condition. And again, we can squeeze this new space into our chain of inclusions, and it fits between uniformly continuous functions and BMO2 in the middle here. Okay. So what's the relation really between BMO2 and BO? And that's also well known. If you take a function which has bounded mean oscillation, and you look at the heat transform at some time t, then you have this estimate here, this Lipschitz estimate here, and the Lipschitz constant is just the BMOT semi-norm. So there's a 2 missing here, and that's the Euclidean inner product, the Euclidean norm. So this means if you take a
Wolfram, we cannot hear you.
Okay, so what I want to say is the following. If you take a function which is uniformly continuous, we already saw the heat transform is a Lipschitz function. If you look at the difference between f and f twiddle, then you can show that is a bounded uniformly continuous function. So in some sense, the difference between Lipschitz and Lipschitz functions and uniformly continuous functions are the bounded uniformly continuous functions. We have this decomposition here, and the decomposition is just the same as before. You decompose in f twiddle t and the rest, f minus f twiddle t. So what that tells you is already the following. If you take an unbounded function, which is uniformly continuous, and then you look at the heat transform, then that heat transform with some kind of average of that function, that remains unbounded for all t, because the difference of these functions are in BUC, and functions in BUC, they're always bounded. So you cannot get rid of the boundedness by taking the average. Which in general is not the case. If the function f, for example, has a lot of oscillation, then this is not true, may not be true. So here's a first result, which is a special case of a more general result with Lu. And it says, if you take a function which is uniformly continuous and you look at the heat transform, then that gives you a flow of real analytic functions. And we already saw these are all Lipschitz functions. And these Lipschitz functions, they uniformly converge if t goes to 0 to that original function f. And you can also control the Lipschitz constants here. Of course, they should blow up maybe if time goes to 0. And they are, for example, controlled by this t to the minus 1/2. And then this BMO 1/4 norm of this function, which is inside here. And in particular, you see that you actually can approximate uniformly continuous function on Cn, not just by Lipschitz function, but even by real analytic Lipschitz function in a very explicit way, just by taking the heat transform. Okay, maybe this is not so very surprising. One small remark is that has nothing to do with the complex structure of Cn. Same thing works for Rn, and you have to modify the proofs a bit, but there's nothing specific about the Cn here. Okay, all of this more or less generalizes to other domains. So we may, for example, replace Cn by a unit ball, the open unit ball Bn in Cn, or even by a general bounded symmetric domain omega in Cn, and then very similar ideas apply in the proofs. Proofs become usually a bit more complex, but you have to think about one thing. The heat flow which you used on Cn has to replace by something else. The heat flow really is specific for Cn. On Bn and omega, you need to do something else. And maybe the natural idea is to look at weighted Bergman spaces on these domains with the standard weights and replace the Berezin transform, the heat transform by the Berezin transform with respect to this, and that works pretty well. So, for example, if you look at the open unit ball Bn in Cn, alpha is bigger than 0. You put a lambda n plus 1 plus alpha. This should be bigger than 0 as well. And then you take a function g on the unit ball, and then you can define a transform which replaces the heat transform by looking at the following integral here on the right-hand side. Gamma is the gamma function, and that is called typically the alpha Bayesian transform of G. It looks difficult, but it's nothing else than just the Bayesian transform of G in an appropriately weighted standard Bergman space, standard weighted Bergman space over the unit ball. That's all here. And a similar thing you can do on bounded symmetric domains. And then if you do this, you can generalize the result I told you before for bounded symmetric domains. So if omega is a bounded symmetric domain, if you don't know what that is, take a unit ball of genus P and you equip it with the Bergman metric. The Bergman metric always is the, or the Bergman metric distance function is the appropriate function which defines the space of uniformly continuous functions on Lipschitz functions here, of course. And then you look at these kind of integral transforms. I told you how they look like in case of the ball. And then they are all Lipschitz functions with respect to the Bergman metric. They uniformly converge if lambda goes to infinity. So now lambda goes to infinity, t went to 0, to the original function f, if f is uniformly continuous. You can still control the Lipschitz constant. They blow up in general if lambda goes to infinity by some BMO semi-norm of f with some constant in front. And again, you have the same result. Also for the bounded symmetric domain, you get a very explicit approximation of uniformly continuous function by real analytic Lipschitz function, and the inclusion is dense. Okay, this was the idea. You pass to, you replace the Euclidean distance by the Bergman metric, and you look at the standard weighted Bergman spaces and replace the heat transform by the corresponding Bayesian transforms. Okay, so I want to use this in the case of the ball later on, and that will play some role. So let me give you some kind of simple application to this in the case of the Fock space, which also generalizes to the ball and bounded symmetric domains. So we saw the Fock space already in the last talk. Here I have an additional parameter t, which will be used later on because I want to do some quantization result. And what I do is I look at a family of Gaussian measures. So this is the Gaussian density, and this constant here in front of makes it a probability measure. And then we already saw the Fock space. Here actually it's a family of spaces, of Hilbert spaces parameterized by t, and it's just the space of holomorphic L2 functions with respect to this measure mu t. So this is a reproducing kernel Hilbert space inside this L2 space here. And it's one particular example of the cases we saw on the previous talk. Then we have the orthogonal projection from the L2 space to this Fock space or Siegel-Bargmann space, which is denoted by pt. So everything depends on t. And if we take a symbol f, which might be bounded or unbounded, then we can form the Toeplitz operator or a family of Toeplitz operator by compression of the multiplication operator. So the product pt times mf, and that's considered as an operator from the Fock space to the Fock space. And if t is a 1, which will be the case on the next slide, I just write tf instead of tf1. And now you can ask several questions about this Toeplitz operator. For example, when is it bounded? Of course, if the symbol is bounded, then it's a bounded operator. This we already saw. However, if the symbol is unbounded, it may still be bounded in general. And this typically happens, for example, if the symbol has very high oscillation, but is bounded at the same time. But if we restrict oscillation, we will see that the operator, the Toeplitz operator, behaves a bit closer like the multiplication operator. So here's a result by Lou and Josh Israelowitz, and it says if you now take a symbol which is in this BMO space, has bounded mean oscillation, it's a priori an unbounded function, it could be unbounded, but not too much unbounded. And then you have 3 equivalent statements. The first statement says the Toeplitz operator with this symbol is bounded. And this is equivalent to saying that the heat transform is bounded for all t bigger than 0. And this is equivalent to saying that the heat transform is bounded for some time t bigger than 0. So what is clear is if the heat transform is bounded at some time, then it will remain bounded for all later times. This is an immediate consequence of the heat of the semi-group property. But what is not true in general and really needs this BMO2 condition is that if the heat transform is bounded at some time, that it's still bounded at earlier times. So it's not easy or impossible to invert or reverse the heat flow and to say something about the heat transform at earlier times from the heat transform at later times. But this happens under this BMO condition here. And there's an equivalent or a similar statement if you replace boundedness by compactness. So the operator is bounded, compact, if and only if the heat transform is vanishing at infinity for all times t, if and only if it is vanishing at infinity for some fixed time t. That's all the same. And now let me give you one simple result. I told you the Toeplitz operator with symbol f might be bounded even if the symbol is unbounded. However, if you just look at UC symbols, uniformly continuous functions, then boundedness of the Toeplitz operator actually is equivalent to boundedness of the symbol. And compactness of the Toeplitz operator is actually equivalent to f being f vanishing at infinity. That's the same thing. And the proof is very simple and uses this approximation result. So let me just tell you how B works. If the symbol vanishes at infinity, then the operator is compact. That's very standard. So I don't want to say anything about this. This is always true. It doesn't use UC. Actually, okay, this is anyway in UC. So assume that the operator is compact. And then we know, since the uniformly continuous functions are in BMO2, we know the following. If we now look at the heat transform of f, then that heat transform is in C0 Cn, not just for one t, but actually for every t. It's always vanishing at infinity. This is what we get from BMO2. Also, if f is uniformly continuous, then the theorem A tells us that the heat transform, if time goes back to 0 or goes to 0, actually uniformly approximates f. And if we just combine these two, then we get the result. So if all these heat transforms are in C0 and they uniformly approximate the symbol f, then the symbol f has to also to be in C0. And that proof somehow works very general. It doesn't, you don't need Cn, you can use bounded symmetric domains. However, if you replace UC, for example, by BMO2, then the theorem is not true anymore. So you can, UC is somehow critical here. Okay, so this was my first application. The second application of this approximation theory are deformation estimates. And here I want to look at deformation estimates and in the sense of refill. And we look at Toeplitz operators on the Fock space still. Later on, we will do the same thing on the ball. And we have this parameter t, which can be seen as a semi-classical parameter, or if you want, it can be seen as the Planck constant or equivalent to the Planck constant, and we let t goes to 0. And then in the limit, we would expect that from the norms of the Toeplitz operators, we obtain the supremum's norm of f, that the semi-commutator in norm tends to 0, and that 1 over IT of the commutator of the operator approaches the Toeplitz operator where the symbol is the Poisson bracket. So these are just these typical estimates in the deformation quantization. Here's the Poisson bracket. I'm sure you all know this. And the question is, when does that work? So does this always work for any f and g, or do you need some conditions on f and g? And there's a first theorem by Borthwick, and it says that if f and g are 4n plus 6 times differentiable on Cn, and all derivatives up to this order here are bounded, then these three conditions are true. This is proved by using techniques from pseudo-differential operators in the Fock space setting. It's a bit strange. So if you look at 1 and 2, there are no derivatives appear here. So there are derivatives in 3. Okay, it might be natural to assume that f and g have some kind of smoothness condition, but there's nothing in 1 and 2. So why should you need any smoothness of the symbols to have such kind of estimates here? The next thing, which is a bit strange, is that differentiation order should somehow depend on the dimension of the space n. So Cn is just a product of C. So that should not really be present here, the n in the differentiation order. And now the question is, I want to look at the limit 1 and 2, so the Toeplitz operator itself and the semi-commutator. What can we say? So how much regularity really do we need for the symbol f and g? And to answer this question, I first want to consider 2. So let me go back here. 2 was this limit of the semi-commutator. This is what we will need later on in our applications. And to study this question, it is useful to look at the big Hankel operator. So what is the big Hankel operator? It looks a bit similar than the Toeplitz operator. MF is the multiplication with the symbol F, and I replace the projection by I minus the projection. So that maps the Fock space to the orthogonal complement of the Fock space in L2. That's the big Hankel operator. And it's a very standard identity that the semi-commutator of Toeplitz operators can be actually expressed as a product of the adjoint of a big Hankel operator with the big Hankel operator itself. So that's just an algebraic easy calculation. It's 1 or 2 lines. So what is the corollary is, if you now have symbols F and G, and you can somehow say that the operator norms of these Hankel operators remain bounded, let's say with the symbol G, and the operator norm of the other Hankel operator, let's say with the symbol F bar, tends to 0 if T goes to 0, then for such pair of symbol, you should have that the operator norm of the semi-commutator, if T goes to 0, actually goes to 0. So these two conditions together with this equality here implies that. So the question is now, you may study, when does the Hankel operator corresponding to the T Fock space, if T goes to 0, tends to 0 in norm? Well, what kind of condition on F do you need? And this is what I want to do next. So here's the first observation. Now we assume that we have a symbol in this BMO2 space, bounded mean oscillation. And we further assume that in some interval, in some time interval, alpha beta, the difference between F and the heat transform at time 2t, so this is the subnorm, is bounded by some constant c. So that should be uniformly in t, where t is in the interval alpha beta. And then the statement is that you can estimate the norm of the Hankel operator by this quantity on the right-hand side. So basically a constant c, which is independent of t, and then the square root of the BMO 2t semi-norm, and then the BMO 2t semi-norm itself. And that now lets you prove when this quantity, the norm of the Hankel operator, goes to 0. And it seems now a bit easier because this is an inequality, a norm inequality of an operator, and you want to prove that the right-hand side goes to 0. That's just an inequality on functions. So functions should be easier than operators. So when is this condition star true? It's certainly true if f is just a bounded function, essentially bounded function, or if f is uniformly continuous, might be unbounded, then star also is true. So for these two cases, which are interesting, we have this condition always. So that means that the problem of when the semi-commutator in norm tends to 0 somehow requires us to answer the question, when a function has the property that its BMO semi-norm goes to 0 if t goes to 0. So what condition on f is necessary? And here's the result, or here's some result. If f is uniformly continuous, might be unbounded, then we already know that the heat transform uniformly converges to f if t goes to 0. So this was this approximation of uniformly continuous function explicitly by Lipschitz functions. But also, if it's uniformly continuous, then the BMO t semi-norm tends to 0 if t goes to 0. So if you restrict the oscillation, then that goes to 0 if the semi-classical parameter goes to 0. So if we use theorem D, which was this estimate of the norm of the Hankel operator by this quantity here, then you know that under this condition, also the Hankel operator in norm goes to 0. And if you recall, the semi-commutator is expressed as a product of a adjoint of the Hankel operator and the Hankel operator itself. You get immediately that if G is a bounded function, or G might be unbounded but uniformly continuous, then in that case, this limit here always is 0 if f is uniformly continuous. So there are a few remarks. If the symbol f is uniformly continuous, it could be unbounded. In which case, for any t, the Toeplitz operator with this symbol is an unbounded operator. This already we saw in the first application. However, the semi-commutator becomes a bounded operator. So this is a bounded operator, even so all ingredients are unbounded, and actually for every t. So we can have this this quantization here for bounded and certain unbounded symbols. So the next remark is we can prove this also for another space. This semi-classical, or this limit, which I just explained, works for uniformly continuous functions. So if the function is continuous, but continuity is not necessary. So we may look at the space VMO-Cn. These are the functions of vanishing mean oscillation on Cn, inside Cn. And this is, just to recall, the following. If you look at cubes E in Cn, and you take a function, then you can look at the average of the function over the cube, which is this quantity here, 1 over the volume of the cube, and then you integrate the function over the cube. And that gives you Fe. This is a constant. So, and then if you look at 1 over volume of E, integral over F minus this constant absolute value, and you let the cube go to 0, the volume go to 0, and that if that goes to 0, then the function is set to be in VMO Cn. So this is a notion by Sarrazin. So one remark is that this space VMO Cn actually contains non-continuous functions. Not all functions there are continuous. And we have the following result. Oops. We have the following result, that this quantization theorem E here actually also works if you replace UC by this space VMO C. But in this case, we only speak about bounded functions. So in this case, everything is bounded. So this is not a more general case, it's just a different case. So you may ask, does this work actually for all L-infinity function? And the answer is no, it doesn't. So for example, if you look at the two symbols F and G bar, which are defined as 1, if Z is equal to 0, and e to the I divided by norm Z square if F is not 0. So this is a very nice function, except in one point, namely 0, where it oscillates very much. So it's, except for one point, is a very nice function. But this one point already destroys the quantization estimate. So in that case, you get that the limit of TG TF minus TGF applied to 1 is -1. So that not even converges pointwise to 0. This operator TGF is actually the identity, because of this here is the identity operator. So that's where the -1 comes. And if these symbols G and F oscillates very much, then that product tends to 0 if you apply it to 1. And that's what happens here. So one point is enough. So let me just say, tell you something about the asymptotic relation 1. When does the Toeplitz operator with symbol F actually in norm tends to the subnorm of F? Do we need anything? The answer is no, we don't need anything. This works actually for every L-infinity function. No oscillation condition is needed here. Okay. So the question is, now we find certain symbols for which the semi-commutator converges to 0 if the semi-classical parameter goes to 0. And you may ask, did we miss something, or is there some maximal space where this works? So I want to explain some kind of converse of this statement in the case of the Fock space again. And here I want to do the following. So I look at these spaces, at these L2 spaces with respect to this family of Gaussian measures, and I take the direct integral of this. And this I denote by L2. So it's the direct integral of all these L2 spaces where t, the time parameter, runs from 0 to infinity. And on this, I consider operators which are direct sums of operators xt. Each operator is a bounded operator on the corresponding L2 space. And these operators are equipped with this norm here. And then I look at the algebra of all these operators where this norm here is finite, and this is denoted by op L2. And inside this algebra, I can find an ideal, a closed two-sided ideal, which I denote by I, and that's actually the space of direct integral operators here, where this limit here tends to 0. It's not bounded, but it tends to 0 if t goes to 0. That's easily shown to be a closed two-sided ideal. And I can do the same thing by replacing the L2 space by the Fock space, this family of Fock spaces, which gives me then a space H2 and operators on these spaces. So direct sums of operators on these spaces, which are op of H2. So the same thing, just with H2 replaced by L2 replaced by H2. And examples of this arise, for example, for Toeplitz operator. Take an L-infinity function, and then you can define the corresponding Toeplitz operator on the corresponding Fock space, and you take a direct integral of those, and that gives you an operator on H2. And you can do the same thing with Hankel operators, and that gives you operators on L2. So you consider you fix the symbol and you consider the operator on different spaces. And now we consider the following set. We look at all functions f, L-infinity functions, such that the semi-commutators of these two operators here, so we consider them, so to say, on all weighted spaces simultaneously, are in this ideal I. And this should be true for any bounded function g. And then it can be easily seen that that actually is not just a set, it's even an algebra. It's a conjugate closed subalgebra of L-infinity. And it can be also seen that it coincides with the set of all f in L-infinity, such that the Hankel operators, hf and hf bar, are inside this ideal. So it's rather easy to see that A is an algebra. It's not that easy to see that this set here is an algebra, but the relation between the semi-commutators and the Hankel operators gives that. And now I want to show you a set of bounded functions, which look a bit familiar. So we may look at L-infinity function such that this BMO semi-norm tend to 0. If t tend to 0. That was an inequality which appeared before, And now the result is the following. This set B actually also is an algebra. So that's not, if you try to prove this from this condition, is not so easy. But what one can see is actually that this set B of functions coincide with A. That's also not so hard. But the thing is that you precisely can characterize what that C-star algebra is. It's the space VMO Cn intersected with L-infinity. So the bounded function in VMO. And so that tells you that this actually is a C-star algebra. And you precisely know what it is. So in that sense, this C-star algebra bounded VMO function is actually the largest C-star algebra for which the quantization estimate 2 holds. So if you have this, if you have a function in this, then this is somewhat the largest algebra really where you have 2. And that result, I'm not sure whether this holds in the Bauer case, and I'm not sure whether this holds in the case of bounded symmetric domains, but I assume probably it's also true. But we could only prove it for the Fock space. Okay, so in the last, how much time I have? 15 minutes maybe. I can explain another application actually of the quantization result, which come from the approximation, now to the topic of Toeplitz algebras over the unit ball. And here I want to keep things as simple as possible, only to look at the 2-dimensional ball. And but many things generalize to higher dimensions. So just to set up everything, I want to give a definition. I look at Bn. This should be the open unit ball in Cn. And I look at the weight parameter lambda, as usual, bigger than -1. And now I form a family of measures similar to this Gaussian measures, but now these are measures on Bn, and we saw them also in the previous talk already. These are the standard weighted measures where the weight is 1 minus norm set or absolute value set squared, and then to the power lambda. This is the Lebesgue measure, and the constant C lambda is some constant which you can write precisely if you want with the help of the gamma function, but it's not important here. It's just a constant which makes this weighted probability measure. And then you all certainly know we have the weighted Bergman space, which now consists of holomorphic function in this weighted L2 space over the ball. And that's again a reproducing Korman Hilbert space. It's a closed subspace of L2, and we can look at the family of orthogonal projections, which now are denoted by P lambda from L2 to A lambda. So this is now takes over the role of the Fock space. And then we have the Toeplitz operator, let's say for bounded symbols. So in this section, all symbols will be bounded, which is the compression of the multiplication operator. So we take a symbol f and we multiply a function in the Bergman space by f, produces an L2 function, and then we project back to the Bergman space. So this is all very well known here. And then, as I said, we can try to prove quantization estimates also in the case of the ball. Now the parameter is not the time parameter t, but it's this parameter lambda, and it doesn't go to 0 as t did, it goes to infinity. and we can try to find symbols such that the semi-commutator tends to 0 if lambda goes to infinity. And now we have to, or it's maybe natural to look at uniformly continuous functions again now on the ball, and bounded function having vanishing mean oscillation inside the ball. But now uniformly continuity and vanishing mean oscillation have to be measured with the help of the Bergman metric distance on the ball. That's the very natural metric there. And then with Raphael Hager and Nikolai, we showed that the very similar thing holds now on the ball. So if you have a uniformly continuous function, or if you have a function which has a vanishing mean oscillation, it should be also bounded here. Then we have this, we have that semi-commutator tends to 0 if lambda goes to infinity. Or this should be not f, this should be g here. And this is true for all g in L infinity or all g in UC. So all combinations are okay. And this theorem we can even prove in the case of bounded symmetric domains, channel bounded symmetric domains instead of the ball, but only in the case of UC symbols. So I don't think we have a proof in the case of VMO symbols. Probably it's also true for VMO symbols, but I think we didn't manage to prove that. That's in that paper with Nikolai and Raphael. And this I will use now in this part. And now I want to describe certain operator algebras, operator C-star algebras on this weighted Bergman space. And the idea is the following. I look at the standard orthonormal basis on the Bergman space over the 2 ball, which is just the set of these normalized monomials here. So this is denoted by B lambda. The norm here depends on lambda. And then I can form a Hilbert subspace of the whole Bergman space by fixing alpha 2 in this multi-index. So alpha 2 is fixed and just alpha runs through Z plus. And that gives us a bunch of vectors, and I look at the linear span of this, and that gives a new space, which is of course a closed subspace, a Hilbert subspace of the Bergman space. It's denoted by H alpha 2. And that gives now an orthogonal decomposition of the Bergman space of that type here. And now I want to describe these spaces H alpha 2 a bit more precisely. And here is a crucial observation. Instead of looking at the 2 ball, we may also look at the unit disk. So we look at the object which has a dimension 1 less. So this is D. And we may look at the weighted Bergman space of the unit disk, and mu now is the weight bigger than -1. Again, we have the standard basis, which now is denoted by B mu. And the crucial observation is the following. If I take one of these elements in the orthonormal basis of the Bergman space over the 2 ball, then I can write it in a multiplicative way as a product of 2 elements in this basis here on the unit disk. However, these elements in B mu are elements with respect to different weights. Here is the weight alpha 2 plus lambda plus 1, and here we have the weight lambda plus 1. So it's an element in the tensor product, if you want, of these 2 Bergman spaces over the lower dimensional domain. And since alpha 2 is fixed, and if you look, if you take a linear span of all of this, we can write the space H alpha 2 in the form f of Z1. So this is a function in the Bergman space over the unit disk in just one variable, but corresponding to this weight here, alpha 2 plus lambda plus 1 times this fixed function here. That's a representation of H alpha 2. And this now gives us a map from this subspace of the Bergman space over the 2 ball to the Bergman space over the disk with this type of weight, which takes this function here and just picks out f of Z1. And that is a unitary operator between 2 Hilbert spaces. So we now, up to this operation, we replace H alpha 2 by this Bergman space over the lower dimensional domain. And now we sum all these unitary operators, and that gives us a unitary operator, which is denoted by U on the full Bergman space over the unit ball to the direct sum of Bergman spaces over the unit disk, but important for different weights. And the weight, if alpha 2 runs through Z plus, they go to infinity. And that will somehow relate the whole thing to quantization. And now the question is, can we find Toeplitz operators with suitable symbols that respect this decomposition, meaning that they leave all these spaces here invariant. Of course, a generic Toeplitz operator will not leave them invariant, but if you have maybe Toeplitz operator with specific symbols, then that might be okay. And what you could do is the following. You could look at symbols of the form here in the third line. So Z is an element in the 2 ball. It has 2 parameters, Z1, Z2, which are complex numbers. And the symbol splits into a function A and B, where the argument is of this type here. A is bounded on the unit disk, and B is just a bounded function on the interval 0, 1. And then it turns out, if you look at Toeplitz operators.
Wolfram,
yes.
may I write that in B in denominator should be modulus Z1?
Here's C1. Yeah, there's a typo. Yeah.
No, nominator. Sorry, nominator Z1.
B of.
Yes, here Z1. I know Z2 or 1 over modulus Z1. Yeah.
So one has C1 and the other C. Yeah. Okay. There's also a typo here. So if you have a symbol of this type, then that symbol leaves all these spaces in the decomposition invariant, and if you after conjugating with this unitary operator U, and you get in each level you get a multiple times the Toeplitz operator on the unit disk. So this bold here always means on the ball, this non-bold operator on the unit disk, where the symbol on the unit disk is A, but it's with respect to a certain weighted Bergman space where the weight, if alpha 2 runs through Z plus, goes to infinity. So this is the observation, and you can also calculate these numbers here, and they are given by some integral which involve this function B here. Okay, so in particular, these operators where you only look at FA and FB, so in the first case B is 1, and the second case A is 1, they commute. This you find immediately from the representation. And now the idea is we want to study C-star algebras generated by Toeplitz operators, which actually leaves this decomposition invariant. So Toeplitz operators with the symbol have the structure as I explained on the previous slide, and study the structure of such C-star algebras. So what we can do now is we can pick A from a certain set in L infinity D, and B in a certain different set, which is denoted by S2 here in L infinity 0, 1, and then look at all Toeplitz operators with the symbol FAB on the Bergman space over the 2 ball, where A runs through this first set and B runs through the second set. And then we look at the C-star algebra, which is formed by all these operators. And this C-star algebra is denoted by T lambda B2 S1 S2. And it, of course, depends on these two sets here. Okay, this is just a notation. C-star of something is a C-star algebra generated by this set of operators here. And the question is, what can we say about the structure? Okay, so time is running a bit, so I will skip the next example and come to one example which is more linked to the quantization, which I explained. And now I want to choose S1 to be all continuous functions on the closed disk, and S2 is just the simple set only consisting of the one function. And then I want to see what comes out of this, what kind of algebra can I get. So I look at the algebra T lambda B2 continuous function on the closed disk and 1, and that I consider as a C-star algebra inside all bounded operators on A lambda 2. And operators of this type here, as I already saw, after conjugation with U, decompose into Toeplitz operators with the symbol, with a certain symbol AJ. And these Toeplitz operator on the disk, they do not commute in general, so this will be a general non-commutative algebra. And the question is, what can we say about the structure? So the first result is the following. If I take any operator, let's say T lambda, in this C-star algebra, this C-star subalgebra of bounded operators on the weighted Bergman space, then I can conjugate this by this unitary operator U. I get something which leaves the decomposition of the Bergman space invariant. And the statement is it's precisely of this form here. So you get a Toeplitz operator with a certain symbol A plus some compact operator. And these compact operators, they converge to 0 if alpha 2 goes to 0. in norm, so they converge in norm to 0. And the observation is that any operator in this C-star algebra has a unique decomposition of this type. So we can assign some function, A, which is the symbol here, to any operator in this algebra. And the question is, if we start with an operator in this algebra, how can we find that function here? And that function should carry a lot of information about this operator. And the answer is, this is related to quantization. And so what we do here on the Bergman space is we look at the Gaussian transform of the weighted Bergman space of the disk, which we already saw in the previous talk. I think everyone is very familiar with this. We take an operator and apply it to the normalized reproducing kernel and look at the inner product with the normalized reproducing kernel. And that produces out of an operator in function. So I don't think I have to go into detail here. And now the thing is that the quantization effect of the Gaussian transform for different weights in these weighted Bergman spaces allows you now to recover the symbol A. So what we do is the following. We take an element, so we look at the following map from this C-star algebra to the continuous function on the closed disk, which takes an operator, decomposes it into a sum of operators on these sum of Bergman spaces, and then we look at the Gaussian transform with the corresponding weighted Bergman spaces of this one here, and we let alpha 2 go to infinity, and then we produce a function which is continuous on the closed unit disk. And the statement is that that map is a continuous surjective star homomorphism of C-star algebras. And you see, you let some semi-classical parameter go to infinity, so to say, and you produce a function, and this is somehow related to quantization. And so this homomorphism now recovers in the decomposition, which I showed you in the previous slide, the symbol A. It's just rho of T lambda. And that gives you a function on C of the closed unit disk. Okay, so what can you do with that? As I said, that function should contain some information, of course, on the operator. And okay, you may expect a similar result to the Toeplitz algebra, which is formed by Toeplitz operators with bounded symbols up to the boundary on the 2-ball. And here we have the following result. An operator in this C-star algebra is a Fredholm operator if and only if the symbol which is picked out by this process is an invertible function on C d bar. So invertible means pointwise non-zero. And in this case, we can also calculate the index, but the index in this case is always 0. We get also the essential spectrum, and it's just the range of the symbol which we pick out by this homomorphism. Okay, so I have 3 more minutes. I'm almost at the end. The next question we may ask about this C-star algebra is, what can we say about the irreducible representations of this? It's a non-commutative C-star algebra, and also the irreducible representations, they can be completely classified with the help of the quantization, so to say. So we get a complete list in that case of irreducible representations. And there are 2 types. First, we have infinite dimensional representations, which are formed in the following way. So we take an operator which is in this algebra here, T lambda, and then it has a decomposition of this type here. And we pick out the level alpha 2 in this decomposition, and this gives us an operator on the weighted Bergman space over the unit disk with this weight here. And that is one type of representation, and alpha 2 runs through Z+. And the other one are one-dimensional representation which come from this quantization procedure. So you may pick an element in the closed unit disk, and then you form from T lambda this symbol O of T lambda, and you evaluate it at T. And this gives you all one-dimensional representation. And the statement is these are of course representations, but there are no others. These are all of them. Yeah. So what are further problems? So this might be maybe an easy case. We may, instead of just looking at the symbols, the symbol set 1, just the one function, add a larger algebra by replacing this by all L infinity function here. So that gives a bigger algebra. And the question is, what can we say about this one here? And there's a lot to say about this, and I do not want to say this in detail because there's no time. But maybe two things. First of all, still we can take elements in this C-star algebra, and we can decompose it according to the decomposition of the Bergman space into a sum of operators. What's new here, if you put this L infinity here, the decomposition is not unique anymore. That caused some problems. Also, we have Toeplitz operators which are Fredholm here with non-zero index now, and we can calculate index formulas. And these are all done in some work with Raphael and Nikolai. We can go even further and try to replace this space CD bar by a bigger function algebra. But in the proofs, what we always need is that we have some kind of quantization result. So we may, for example, replace this C-star algebra by the function algebra of functions vanishing at the vanishing oscillation at the boundary. And in this case, we have two effects here. First of all, VO delta, I did not define this, but this is in this function space admits also quantization, and also it admits compact semi-commutators. So based on these two results, we can, in a very similar way, study the corresponding C-star algebra of this type here, and even the C-star algebra T lambda B, where we take the first symbol set to be L infinity, and then the other one to be VO delta, so vanishing oscillation at the boundary of the unit disk. In a similar way, things become more complicated at each step. The algebras become larger, but there's a lot of interesting mathematics behind. And of course, you may ask what happens in higher dimension. In higher dimension, you have a lot more flexibility to decompose the Bergman space, and you have a lot more interesting operators. You look at an operator algebras, you have to look at, and symbol classes, and we did some part of this, but I think there are many cases which we do not treat, and there are many open and interesting problems and a lot of mathematics to discover, especially for the young people with a lot of energy. And I propose that as an interesting problem to look at it. Okay, I think now I'm 1 minute over time. Time is up. Let me give you just a few references in the end. So there are 5 references. The first one with Lou is on this approximation results. In the easiest case for the Fock space, but then we did it also for the bounded symmetric domains. The red ones are on quantization. The first one is in case of the Fock space, where we get a bit stronger result. And the second one with Nikolai is a generalization of this on bounded symmetric domains, where the domain is more complicated. We don't have kernels, so we have to work around things. We don't have semigroup properties, and we get a bit weaker result. But this result might be possible to get better ones. And the second two papers, the last two papers, are actually on algebras and essentially extend what I explained in the last part of the talk. Okay, I think that's all. And so congratulations to the 16th anniversary of Simulstuff, and thanks a lot for listening.
Thank you very much, Wolfram. Thank you very much. Very nice talk. And please, questions, comment now.
A question.
Yes.
That you just discussed about the 2 ball. Do you have corresponding results for the n ball?
What I explained in the last part?
Yeah. So this third part of your talk, this kind of results, do you have corresponding results for n-dimensional ball, or
yes.
Is this just for the?
No. As here, the last two papers. So the last one, I have to think. Maybe the last one. Please, Nikolai, correct me. Deals with the 2 ball.
Yes,
but
it's with Raphael and
the
you.
second last one deals with
Yes,
actually the
second,
n-dimensional unit ball and a lot more general, somehow more general setting than what I explained.
So this paper that now adds Raphael kind of extends the previous paper to the n-dimensional ball?
To the n-dimensional ball, yeah.
Okay.
But there is nothing for bounded symmetric domains in more general.
Yeah, that was my other question.
Yeah.
Do you think there is any hope of considering other bounded symmetric domains, maybe?
This was actually a question I should ask you.
Yeah.
So you would need the decomposition.
For bounded symmetric domain, we do something related to quantization in this red paper.
Yes, we have the quantization result. That works well. But then we need to do these things. We need somehow decomposition of the Bergman space. And we need to find symbols of the Toeplitz operators
here,
that leaves everything invariant. And then, so somehow we have to reduce the dimension. So here we reduce the dimension from the 2-ball to the unit disk, and then somehow use the quantization on the unit disk. So if one can do something on the, and also, by the way, it also works, as I learned from Nikolai, for the Hari space in a nice way. So if you could do this for the bounded symmetric domain, somehow reduce the dimension, then use quantization result there, then that might be possible, but we haven't done anything like this.
Raul, once we discuss with you how to reduce dimension with bounded symmetric domains using this unitary operator, but we failed to see something.
Some intuition for this. I'm wondering that maybe this reduction of dimension that you did for the 2-ball and the n-dimensional ball is some kind of isotypic decomposition for a small group. So maybe if you follow this idea, you can do something for bounded symmetric domains. Mm-hmm.
But here, if you reduce dimension, you get another bounded symmetric domain. So you go from 2-ball to 1-ball, to say, and then use the results there. So this is also important.
So
and the weight need to go to infinity. To have
you would need an isotypic decomposition that brings other bounded symmetrics into play. Yeah.
Yes, exactly.
Or you need, if you don't have this, you need to do something else. Yeah. So probably first you need a good decomposition, and then you need to decide what to do afterwards. But it gives I think it gives a whole bunch of interesting C-star algebras where you can do a lot of things, calculate index theorems and spectra and so on. And it's a good field to play with.
You know, one of the idea behind this decomposition is lie in symbols that are invariant under some subgroup of biholomorphism. So maybe one need to look at that direction.
Yeah, that was precisely what I was saying. That somehow, this decomposition seems to be the isotypic decomposition for the action of a subgroup of U2 in this case.
Yeah, but you know, you need to then to build of this isotopic subspaces some Bergman space or some other bounded symmetric domain of low dimension.
It's not just a decomposition of the domain; it's at the same time a decomposition of the space. So the orthonormal basis, or some good set of orthonormal basis, should also behave in such a nice product way, or somehow. I think you need to find a good relation between orthonormal basis between these domains to apply this idea. But it would be interesting to see other examples.
Yeah. Other questions
for the talk?
Oh, Raul, you would like to say something more?
I was just thanking for the talk.
Thanks.
Hopefully we will have soon links to the audio recording of the talk, and we can think more repeating this talks. Okay, if no questions, I would like
maybe
to
there is I see a hand, but Jimenez.
More questions?
Yeah, can you hear me?
Yes.
My question is, there is an area in quantum mechanics when all this knowledge is applied?
Yeah, I mean, if you look at semi-classical, I mean, in quantum mechanics, if you look at semi-classical limits, then I mean, there's a lot of research on these type of things, not just how the operators behave in the limit, but also how evolutions by these operators behave in the limit. And there's a whole machinery behind this. And I mean, these Toeplitz operators, these are maybe some very classical examples where you have this quantization. You may look at this in the Schrödinger picture or in the Fock-Bargmann picture.
Okay, so I need to go to the website and see again the conference.
It might appear in few days. In few days, this talks will be available via web page of the conference.
Thank you very much for your time. Have a nice day.
You're welcome.
No question more? Okay, so I would like to thank, first of all speakers and all audience for the attention to this conference. And well, let's see each other in 17th birthday of this investor. So thank you to all. Take care and bye-bye.